All right, thanks for coming, guys. And for those of you who are online watching, which is more than we have in the room, I'd like to introduce Lloyd Watts. He's an old friend of mine from when he was a grad student at Caltech, and we worked on cochleas together, electronic analogs of human hearing. And Lloyd did a cool thesis on wave propagation in the cochlea that leveraged a bunch of physics stuff like WKB approximation and stuff like that, which had something to do with you getting into this physics stuff, I think. But anyway, and then he went off and worked at interval research, and then took some technology he was working on there and started Audience, and which turned into a big company doing noise reduction for cell phones and stuff like that. And retired from that, and now he's amateur physicist, I guess. Right?
I guess that's one way of saying it, yeah.
So tell us about that.
Okay, thank you very much. So thanks very much for setting up the talk. I'm trying to go after an old unsolved problem, but it's an old unsolved one that I think has perhaps been forgotten, or perhaps people are not aware of it anymore. It's so old that it's not top on anybody's list. But nonetheless, there is an old unsolved problem that I think might be a gateway to some new physics. So that's why I went after it. Not just that I wanted to go and dot an I and cross a T from 87 years ago. I think if we get that right, we might find some new physics that we can get access to because we have it. So this slide here is, I'm going to walk you through the history and the sort of the problem statement. So I assume that physicists in the audience are, of course, familiar with the Schrodinger equation and the Dirac equation, but I'm just going to recapitulate those things. So the Schrodinger equation is the first access point in quantum physics where you get the energy levels of quantum transitions that are often used to explain, for example, the hydrogen spectrum, the observed hydrogen spectrum. So this first diagram here is showing the energy spectral levels of the hydrogen excited states, the ground state here, n equals 2 and n equals 3 states, and of course there's an infinite number of those states. There's a usual 1 over n squared law that describes that spacing of energies, and in the early 1900s that was adequate to explain what was observed. So Schrodinger Hydrogen Atom explains the basic energy levels, but it doesn't explain spin or fine structure, and it has wave functions with cusps at the origin. So now when I say that, that may seem an unfamiliar statement. I haven't seen anybody ever in the literature comment on that or complain about it as a problem, but it's related to the problem that people have commented on in the Dirac equation. So let me say what I mean by cusps at the origin. For example, the ground state has the simple is of the simple form e to the minus r over a naught, where a naught is the Bohr radius. So it's a simple decaying exponential going up from 0. R is on the semi-infinite scale, going from 0 to infinity. But if you took a slice through the atom and you looked at it sort of coming in from the left and going out to the right, what you'd see is a decaying exponential in both directions. So at r equals 0, you've got a decaying exponential going out on this side and coming out on the other side, and there's a peak in the middle where they both come together, and that's what I'm talking about, the cusp. There's a slope discontinuity at the origin, and it goes out in all 3 dimensions, but there's a slope discontinuity in the simple form of the Schrodinger solution. Now, no one ever comments or complains about that, but it's an existing problem. Now, when you go to the Dirac equation, people advance to the need for the Dirac equation because, in fact, the simple spectrum as predicted by the Schrodinger equation doesn't explain something that was, in fact, observable spectroscopically in the 1920s, which was the fine splitting. If you actually looked at any of the upper, of the spectral lines, you could see actually that there weren't just simple spectral lines, but there were little pairs of lines. There was a little splitting of those lines. You had to zoom in to 1 part in 100,000 to see those little fine split, but they were there and measurable even with the optics of the 1920s. The Dirac equation beautifully explained that and explained spin from first principles, whereas Pauli had been just sort of attaching it ad hoc onto the Schrodinger equation. And Dirac equation explained antimatter, all in one, in one fell swoop, explained all of those things. But now, instead of just having a cusp at the origin, it now has a singularity at the origin. That was commented on by Charles G. Darwin, not the famous botanist, evolutionary, evolution scientist, his grandson became a quantum physicist in the early 1920s, and he did one of the first wave function solutions of the Dirac equation. Dirac did the theoretical work, and then Darwin was one of the few people right on there who did the form of the solution, including the wave function. And he observed in the final solution, I'll show in a minute the expression, that there is a singular term. There's a r to the minus something in there. And he commented on it in the paper. He said, clearly this is singular. He was a wonderfully frank scientist. He said, basically, I don't really know what to make of this. And what he said was, this would probably go away if we could do the two-body problem properly, because we're assuming an infinitely heavy nucleus and a point charge, and all of that's leading to nothing moving in the middle. So, but if you allowed things to move, you could probably solve it. So he basically said, probably don't worry about it, and look, it gets all these energy levels right. It's a tour de force. So that was the beginning of leaving this problem unsolved. It looks kind of small. Now, if you look in the literature from this point forward, I haven't really seen anybody mention the singularity of the Dirac equation wave function until you see there's a textbook. It's Itzikson and Joubert, a 1980s vintage textbook, which describes how to solve the Dirac equation and what the wave functions look like, and comments on the singularity at the origin. And what he says was, because this exponent, the 1 over r, is a very small number, 1 over r to the 0.005. So it's not 1 over r, a familiar singularity. It's this strangely almost unity function, except right at the origin. So that's an actual plot of the function, and that small exponent means that it's very tightly localized. Right? So Itzikson and Joubert basically say it's singular, but only in a very small region, which is kind of like saying yes, it's singular, but it's a small singularity, so don't worry about it, right? That's the last time I see in the literature that it's mentioned. There's an awareness in the literature there's a problem, and it's part of the pedagogical literature, but then not discussed any further. Okay, so this is the picture up to Dirac. That takes you to 1928. Now, at that point, it basically explained the data that we had in 1928. By the 1940s, microwave technology had allowed Willis Lamb and his student Rutherford to do finer measurements of these energy levels, and what they saw was then a slight misprediction here. The Dirac prediction says that the 2s1/2 and the 2p1/2 energy levels should be identical, because the expression for the energy depends only on n and j, and both of them have 2 and 1/2 as the quantum numbers there. So those are basically energetically identical in the Dirac theory. Well, so he did a beautiful experiment that measured, are they really the same, by forcing a transition to the two of them and measuring the difference. And he measured the small difference of about a gigahertz when the measurement is done, expressed in terms of hertz. This number down here it's about 1 million gigahertz. 2 million gigahertz is the actual transition energy level. So it's about a 1 factor in 100,000 difference. Sorry, it's about 1 in a million difference is this small thing called the Lamb shift. Okay, so this extra information on the slide then shows the small difference shown there, the shift of the 2s1/2 state, and there's a corresponding shift in the ground state that is not explained by the Dirac equation, and it required a whole new theory to explain that small energy shift. So the Lamb shift was an important experimental result, and it caused Feynman and Schwinger and the famous physicists of the 1940s and 50s to build a whole new branch, basically a new branch of physics, quantum electrodynamics, to explain that 1 part in a million experimental error. So that was a big deal. In explaining it, and now the expression for the leading term of the Lamb shift is shown down here. So you see that we have these 3 expressions for the energy: the Schrodinger energy, the Dirac energy up here, and then the tiny correction associated with quantum electrodynamics that gives the full picture. So now, by the time that was done, it was heralded as a massive achievement. It was a massive achievement. It now pretty much explains what we need to know about quantum transitions. Victory was essentially declared, although there was grumbling by Dirac himself about various problems with infinities and renormalization in this formalization. But one thing that they never did go back and look at was you still have the singular Dirac wave function. Quantum electrodynamics never says anything about how the wave function is affected by quantum electrodynamics. It's a way to compute the energies. So by focusing only on the energy, they've left a problem unsolved since 1928. But what about the singular Dirac wave function? It's not a physical result. It can't be that way. Something must tame that singularity of the origin. But no one ever says what it is. So that's the purpose of the work, is to explain what happens to the Dirac singularity that has, as far as I know, has never been explained in the literature. So the question is, can we find the quantum electrodynamics compatible wave function that is compatible with the Lamb shift? So now, before I take you through the details of how we find a solution there, just what's the importance of this? Why do we care? It's an old problem. People have apparently not thought it was important enough to go back and fix it. Why should we seek this QED compatible wave function? The first part of it is pedagogical. I mean, as I was studying this, it was irritating to have this problem pointed out from nearly a century ago, and then the field advanced into apparently a solution that left this problem unsolved behind it. So explaining it to new students, it's just simply unsatisfactory to not have that thing properly explained. But that's not the reason that I went after it. But the reason I went after it is because I believe that it may be revealing something about electron dynamics that we can't otherwise know if we don't know what the wave function is. And in particular, we can't understand, at least I believe it may be possible, that we can't understand a quantum transition, the process by which a photon is created from a change in energy levels of an atom, without a deeper understanding of what is happening with the wave function. Now, so that's the motivation that actually drove me into studying it, is that I really wanted to understand a quantum transition at a level of depth greater than just saying it's a axiomatic event with an annihilation and a creation operator. Dirac collapsed that down into a single event that there's no physics that goes below that. I think that there may be some kind of wave-oriented physics that goes below that. And that's what drove me into trying to study it. So what we're looking for is the corresponding wave function that goes with quantum electrodynamics that would look different from the Schrodinger and Dirac wave functions without either the cusp or the singularity at the origin. So I'm going to take you through just the terminology of what's in the Schrodinger and Dirac equations, so that when we come to the new work, the numerical methods, you'll have a context for it. So here is the Schrodinger equation that includes the usual Schrodinger terms, but also the potential that connects the electron and the nucleus. And that's traditionally the Coulomb potential. It's a 1 over r potential, a 1 over r squared force. And it's shown there, V of r as a 1 over r form. In order to solve the Schrodinger equation, they do separation of variables. They break it up into a radial and angular components. This is the radial equation that results. You can find the energy, the 1 over n squared form that we saw earlier, and this is the elucidation of the closed form solutions, well known. This is undergraduate level stuff. But here's where we have the e to the minus r over a naught term that I mentioned before. That's the thing that gives us the cusp at the origin. And where does that come from? That comes from the singular Coulomb potential. It's because we have 1 over r potential, which goes to negative infinity at the origin, that we then have a cusp with a slope discontinuity at the origin. So the Coulomb potential is basically at the root of the problem. We put a singularity into the problem with the Coulomb potential. We should expect some trouble at the origin in the solution, and we find it. Okay, so that's the Schrodinger hydrogen atom. The Dirac equation, the Dirac formulation has a parallel development. This is the more complicated form of the Dirac equation. It's now not just using simple scalar variables, but now these A quantities, AX, AY, AZ, and beta, are non-commuting matrices. If you're not familiar with that, don't worry about that, but just to show you that there's an additional complexity of it. The Dirac equation is essentially a four coupled one-dimensional equations. And that's what allows it to predict spin and antimatter. So anyway, this is sort of the form of the Dirac equation. It still uses the Coulomb potential for the hydrogen atom. When you do separation of variables now, it splits into these two components, the upper and lower component. This is effectively the electron spinner and the negative energy spinner, or the positron spinner. So it basically, Dirac predicted simply by solving this new equation that there had to be a matter and an antimatter component. And this was predicted prior to the discovery of the positron. So unlike not just purely explanatory of existing measurements, it predicted a thing that had not been yet discovered and was discovered a few years later, in 1930. So it predicts spin, antimatter. The upper and lower component further split out into what's called the F and the G forms of the radial equations. That's F is the upper and usually called the large component, G is the small component, and then there's a radial term, the spinner. When you split that out into the radial equations, now instead of a single second-order equation like we saw in the Schrodinger case, now we have two coupled first-order equations. You see that the F term, there's an F prime, there's an F, and there's a G in the one equation, and the other one has a G prime, a G, and an F. So it's two coupled first-order equations rather than one second-order equation, and both of these are in the context of these complicated spinor elements. So this is now the problem to be solved. When they were able to solve this, to me this is amazing, but they were able to solve this in closed form in the 1920s. They got the closed form solution for the energy levels, much more complicated expression, but extremely close in value to the simpler Schrodinger values, and predicted the degeneracy, the various forms, the fine splitting. It was a tour de force. It predicted just a remarkable number of things. Now, I'll show a couple of other things here that we will need later. If you look not just at the general expression for the radial equations and the energy levels, but you look at the ground state equations. This is a summary of everything you would need to do a numerical simulation of the Dirac equation. You can solve it in closed form analytically, but you could also solve it numerically on a computer, and you would basically need the two equations that we described up here, but now they're in the form where they're using the potential in this form, the 1 over r terms, but in terms of the Bohr radius A naught and the fine structure constant alpha. So this line here is saying the same thing as that line there. The cursor is keeping up with me. It's just the variables are in a more convenient form. So we have the two first-order equations, the boundary conditions that the wave function must go to 0 at infinity, and the normalization condition. So those four equations are what have to be solved, and for the ground state, that's the energy of the ground state. When you solve that for the ground state, you end up with this form of the solution. If you look closely at it, you'll see the e to the minus r over a naught term that was present in the Schrodinger equation. So basically, both Schrodinger and Dirac have the broad characteristic is a largely decaying exponential form. That's the dominant term. They both have that. But then, if you look here, you see that there's also this 2r over a naught to the minus 1 plus root 1 minus a alpha squared term. That's the thing that's of the form, it's r to the minus something very small. Because basically this term ends up having a value of approximately minus 0.005. So that's the thing that gives you the singularity, and the fact that it's got such a small exponent makes it so tightly localized. So we still have not just these cusp, but we have the singularity now. The singular Coulomb potential leads to the singularity in the solution. Okay, so that's the basics. The last place where there's a wave function and the place where the problem is basically left in the field. So now quantum electrodynamics was developed in 1948, Feynman and Schwinger and others. So now I'm quoting a modern, 2007 vintage textbook by experts in QED. The way that they introduce the subject of Lamb shift is by describing, what's the small change to our thinking now that results in that tiny shift in the energy that breaks the degeneracy of 2p of 1/2 and 2s 1/2. So I'll quote them. According to QED, an electron continuously emits and absorbs virtual photons, and as a result, its charge is spread over a finite volume instead of being point-like. So what does that mean? It's kind of an incomprehensible explanation, but if I may, here's how I think about it. It's sitting there, kind of like a dust speck in the middle of the air, and there's Brownian motion. Instead of being bombarded by atoms in the air, it's interacting with both itself and the vacuum in quantum electrodynamics. Now, that's a part that it's very non-intuitive, how it could be interacting with itself, how it could be interacting with the vacuum, but that's the explanation that is given by quantum electrodynamics. They have a long formal development of how they compute how much energy is being delivered and absorbed and released when it interacts with itself through these virtual photons. But the net result is, if you have a point charge electron, they're basically saying it can't just sit there in space. It's jiggling. And it's jiggling in a way that gives it a little distribution, little radius. So it's no longer...
This is small compared to the wave function?
Yes, yeah. Very small. So sub-Compton wavelength, right? So the Compton radius is basically there's sort of a baseline size below which it becomes difficult to talk about what's happening in there. It's so small that the energy levels now become comparable to the mc squared of the electron, and so effectively they're saying a whole new physics happens down at this low, small scale, and I've had conversations with people where they say it doesn't make sense to talk about what's going on in there. It's a whole different kind of physics. Nonetheless, this textbook is giving this explanation, saying it's basically jittering the charge, so it's no longer a point charge, that there is a charge distribution that has a non-zero width to it. So they give an estimate of what that width is, and they say that the finite radius of the electron generates a small correction to the Coulomb potential. Well, the Coulomb potential was the thing that was going, 1 over r. That was going to minus infinity.
But that's the potential that comes from the proton in the middle of the atom, right?
It comes from the distance between the proton and the electron. And so if you now jiggle this side, you're basically saying the electron is jiggling so that it has a distribution. Now, what is the distance now from this jiggly thing to this stationary thing? At large distances, the jiggle doesn't matter. But when you get really close to 0, now the jiggle does matter. And now now you have to deal with the fact that there's a distribution. It's 2 point charges at a perfect distance to each other no longer makes sense when you get close to the origin. That's the essence of quantum electrodynamics had to build in a charge distribution, which is exactly what Carver was saying. It can't be a point charge, so there must be a distribution. And effectively, that's what they're saying. The finite radius of the charge distribution of the electron generates this correction to the Coulomb potential. They then say the respective correction to the energy levels is given by a perturbation analysis of this. And therefore, the finite size of the electron leads to a shift of the electron energy levels, which is what we observe. So they basically gave this informal development of the process. There is a more formal development. It was done originally by Hans Bethe and then formalized by Feynman. But this is kind of the way they explain to undergraduates, here's how to think about it. Okay. So the question is, what is that charge distribution then? They never say what the charge distribution is. Is it it could be a uniform distribution inside a sphere. It could be a Gaussian distribution. Could be a disk. Who knows? What is it? They never actually say. If you could say what the charge distribution was, you could actually compute the shape of the modified Coulomb potential, and therefore you could compute the modified wave function. And it seems as though there's been no interest in actually following that process through. They simply say it effectively jiggles, you get an effective distribution. They always talk just about the mean squared radius of that distribution. Now, what that suggests to me is that they're thinking of it in terms of a Gaussian distribution, because sort of the mean squared. It's a natural way to think about it. It's jiggling. It's never going too far. So the implication of R squared suggests Gaussian distribution inside the Compton radius. And if you do all that, it's consistent. It leads to results that are consistent in a perturbation analysis with the Lamb shift. So what I wanted to do is say, well, then now can we actually follow that all the way through, compute the modified potential, and then compute the modified wave function? And if we do that, it should eliminate the singularity and the cusp in the Dirac wave function at the origin. So that's the agenda. So now I'm actually going to do that. Now, what we don't have is a specific form of the charge distribution. Like I said, could it be uniform distribution inside that radius or Gaussian? We don't simply know what it is. So what I did, since we don't know what it is, I said, okay, I'm going to try every distribution I can think of, so that I can then show, is there something, do they all behave approximately the same? If they do, then we may have something that's likely to be generally true. I'm not in a position to prove anything yet. I'm simply saying every distribution I try results in the same basic behavior. It suggests that the basic behavior should look something like this. So that's the approach I'm going to take. So I'm going to walk you through in a little bit of detail the first choice of distribution, but then I'll show you a summary of all the others, show them how they plot, and you'll see that they behave the same. So the first one that we'll look at, the first charge distribution candidate, is inspired by David Hestenes' work. I'm not sure if you know about his work. He basically made a name for himself in physics by studying the phenomenon called Zitterbewegung. That doesn't ring a bell to anybody. Okay, it's basically Schrodinger did an analysis of the electron and said that there's a high frequency jitter term in here that's suggestive of it's moving very fast in a very tight radius. And that was observed in 1928. So now quantum electrodynamics says, hey, it's moving by absorbing photons, so it's quite natural to say, hey, maybe Schrodinger actually saw, the math said it's jittering in this tight radius. Quantum electrodynamics requires it to move fast. Maybe those are the same thing. So there are two guys, Hestenes and Barut and Bracken, that tried to do a Zitterbewegung analysis that would try to explain, connect the jittering with the Lamb shift. So Hestenes had basically an entire career around reformulating the Dirac equation using his method called space-time algebra. He kind of put it into new variables that split it out into the spin terms, a radial distribution term, and some other terms. But he basically said, what I think is happening is that the electron it's moving in a circle, which would explain spin. That's why it's jittering, not just in random, but it's moving in a circle. And if it's moving in some frame of reference with constant velocity, it's moving on a helix. It's a little corkscrew motion. Right? And based on his calculations, he said, in order for this to be consistent with Zitterbewegung, the radius of that distribution would have to be lambda bar c over 2, where lambda bar c is the reduced Compton radius. So the Compton radius is h bar over mc. Is kind of the basic length scale for the electron. So that's called the reduced Compton wavelength. It's about 10 to the minus 14 meters. So it's a particular size. It basically makes it about a factor of something like 100 or so smaller than the Bohr radius, and about a factor of 100 larger than the proton radius. So it's kind of in between those two scale benchmarks. So it's a lovely idea. Hestenes is saying, I'm looking for motion, a small motion, and he basically makes this prediction of the size, that it's half reduced Compton wavelength. So now I said, well, let's imagine, suppose you have this corkscrew motion, but now the electron is doing that as it moves around the nucleus. So what would a fast spinning corkscrew look like if it was going in, revolving around you? But also, because of spin 1/2, precessing as it moves. So it's like a precessing gyroscope that as it goes around you, it doesn't just sort of stay like this and go. As it goes around, it also rotates slowly. right? So if it's doing that and going fast enough, my conjecture is it would look to you like a sphere because it's constantly
its radial
it's a
distribution,
spinning
it's a
disk
spherical shell.
as it goes around it, right? So it becomes a spherical shell. So now Hestinus didn't ever say that, and I don't want to put words in his mouth. He said helical path when moving in a straight line. But I say now, I take the idea further, if you have it go around, it now looks like a charged shell of radius RZ. RZ, he called it RZ for Zitterbewegung, the Zitter radius, he called it. So that then leads to a charge distribution that would say the electron now looks like a little sphere of charge, a spherical shell of charge. And now, you can analyze that. That's sort of undergraduate math to look at what is the potential as you bring a charged sphere close to another point charge. You can do that math, and that leads to a modified Coulomb potential, which is just this is the oldest cutoff potential ever. 1 over r goes to minus infinity, and if you say I want to cut it off, you just pick a radius and you say I don't allow it to go below that point, and it becomes flat. That's actually what you get if you have a charged shell. Now that was first analyzed by a guy named Wannier in 1943, and the form of it, instead of q squared over r, it becomes q squared over max of r and rz. So basically it looks like 1 over r until you hit rz, and then now you hold it there. So this is basically the clip function, and I'll show you what the pictures look like, but it cuts the thing off. So that's the first one. It's an easy one. Now, I was so excited when I first saw this because I thought, oh my gosh, Hestinus may have this explanation, the Zitter radius being the half-reduced Compton radius, and he never connected it to the Lamb shift, so I did the perturbation analysis hoping and expecting that it would just explain the Lamb shift. And so there's this big blueberry pie in the windowsill that no one's ever found. Oh, it's that easy, Miller time. It didn't work out that way. So I did the analysis, and it predicted a Lamb shift that was way too large. It's like a factor of 5 or something too large. It was sort of in the ballpark, but not quite right. So then I said, well, okay, either Hestinus has overestimated, or my understanding of Hestinus has overestimated. So what do I have to do? How would I scale that radius down? What radius would I need in order to explain the Lamb shift? So I just typed in smaller, and I did guess and check until I finally got that number, 0.38126 times Hestinus's original estimate, lambda bar c over 2. That's the scale factor that makes it actually agree with the Lamb shift. Okay, so we've got something here now. It says lambda bar c is the kind of one person's theoretical prediction, but now to match the data, we need a smaller distribution than that, if it's a spherical shell. So that's the first candidate. I don't know if that's the correct distribution, but it did have basically a highly qualified quantum relativistic quantum physicist spent his entire career doing that. And this is a very credible person who devoted his life to trying to further that line of reasoning. So it's at least a reasonable candidate. I didn't just pull it out of the air. Okay, so now his prediction, just to kind of summarize then, that his prediction said lambda bar c over 2. What we found to match Lamb shift was lambda bar c over 2 times 0.38. So about a factor of 1 over 2.6 smaller than what he seemed to predict. But he never tried to connect it to Lamb shift. So it's not like he made a mistake. It's just the connection suggests it has to be smaller. So now, that thing that we just discussed is the charged shell distribution, and there's the summary. There's the charged shell distribution, the delta function with radius rz, and the corresponding max function in the, where's my cursor? There we are. That corresponding max function there. So that's the one we just talked about, and we see in that line it says rz is that fraction of lambda bar c over 2. Okay, so that's that line in the table. Now you see that we've got 3 other lines. Those are other distributions that I could come up with. Gaussian is one of them. Exponential charge density is another. And there's another one, the Zitter-Bewegung imaginary ring. I didn't just pull that one out of the air either. That's from Barud and Bracken, who did another deep analysis of Schrodinger's Zitter-Bewegung equations and said, if you look at it in this new way, this gets into the deep relativistic physics. It's beyond what I was able to understand, or that I could develop myself. But what they said was the math suggests that the electron is having a complex motion in two auxiliary spatial dimensions, right? A circular motion in these other two spatial dimensions. So now I take that further. I say, okay, so that means in the real spatial physical 3 dimensions we have, the distance is 1 over r, but it's in these other alternate, the imaginary dimensions, it's got another radius. So even when you get right to on top of it at its center of mass, in these other dimensions, you still got a distance of rz. You never actually get to be right on top of that. That would explain why, how there's no singularity. You never get to have the electron and the protein in the same place because in these other dimensions, they have a distance from each other. So when you do that assumption, you get now, instead of 1 over r, you get square root of 1 over r squared plus rz squared. So so that was another popular cutoff Coulomb approach. If you had a Coulomb potential and you couldn't stand the fact that it went to minus infinity, like your computer programs were seg-faulting, then you could always put in a r plus delta, r plus epsilon, right? And that gives you one type of limitation, or you can put square root of r squared plus epsilon squared. Those are softer ways of rounding off that thing at the bottom. So mathematicians have been exploring that for a long time. The Patel and Bethe were the 1970s mathematicians who explored this form, and they called it the truncated Coulomb potential, whereas Wannier did the cutoff Coulomb. That's a hard cutoff versus the truncated. So anyway, if you do those two, now for the imaginary ring, you find again, in order to make it match the Lamb shift, you need lambda bar c over 2 times something small, 0.08. Similarly, if you do a Gaussian charge density, you can make it match Lamb shift. You get a new form of the modified potential, also rounded off, but it comes now with the shape of an ERF function, the error function. I'll show you I'll plot these for you in just a minute. But all of them result in a radius that is lambda bar c over 2 times something smaller than 1. So they basically are all saying that it's a sub-Compton size. But if I talk about Compton size being Hestinus's prediction of lambda bar c over 2, use that as a baseline, everything ends up being smaller than that to explain the Lamb shift. Here's a plot of the functions. So let's, for example, the purple one there that I'm pointing at is the Gaussian distribution. And you see that, so there's the familiar Gaussian distribution, and where are the reference points? The dotted gray line there is lambda bar c over 2, and the gray line on the other side is minus lambda bar c over 2. And you see that that purple Gaussian fits nicely inside lambda bar c plus or minus lambda bar c over 2. So it's fair to call that a sub-Compton radial distribution of the charge. Similarly, the exponential distribution looks like this. The ring distributions for the charged shell look like the red line, and the black one is the Zitterbewegung imaginary ring. So the common element of them all is that they all fit inside the half-reduced Compton radius. So that's why in the title of my talk I said the connection between Lamb shift and sub-Compton electrodynamics. Now, as far as I know, this may seem strange, but as far as I know, I've never seen anybody say that Lamb shift is the result of sub-Compton electrodynamics. The quote that I gave you from Ides, Grotch, and Shaljuto does give you an expression for it, but they never actually calculate it, they never say how big it is, they never compare it to any reference. So this is just kind of a pedagogical point, but at least for the first time somebody is saying, here's how big that distribution would have to be. Regardless of your choice of the shape of it, it's got to be sub-Compton. So that's one of the things that was in the talk. So this all charge distribution candidates must fit inside the half-reduced Compton radius to map to Lamb shift. If you now look at how these correspond to the Coulomb potential, each one of them in their own unique way cuts off the trajectory down to minus infinity. So the first one, the charged shell, which lead to the hard cutoff, is shown there. The red line just follows 1 over r in until it hits the radius, and then it's just a hard cutoff. And so you see that the red line across is the hard cutoff. That's Wannier's cutoff potential. The imaginary ring is the black line, which follows the 1/r curve a lot further down, but it has that rounded bottom because it has the square root of r squared plus rz squared. So that's another familiar one. There's a group up in Canada, in I think it's McMaster University, mathematicians up there that appear to have spent their career doing the mathematics of these truncated Coulomb potentials. So a whole field associated with using that, but with just using it as a mathematical assumption to eliminate the singularity, no physics underneath it. Just we need a way to cut it off, let's use it. Right? Well, that's a justification for it. Similarly, if you have the Gaussian distribution, it leads to this more shallow form of the cutoff, and the exponential distribution leads to that one. Okay, so they all eliminate the singularity. They all do it in slightly different ways, but they're all, again, contained. The deviations from Coulomb are all well contained inside lambda bar c over 2. None of them deviate outside that boundary. Okay, so now we're halfway there. We've assumed a form of the charge distribution, assumed several of them, and found that the modified potentials all behave in a tamed way. Now the question is, can we follow that into a modified wave function? So this is the numerical. So now we'll do the numerical results using these modified wave functions. So
you're able to get to the lambda shift energy levels from these potentials without a wave function, right? So
right.
You were able to fit the radii from some other calculation. You didn't show us, but that's some standard calculation.
It is a standard calculation, yes. That is this last step, where it says, which agrees with lambda shift when that's actually a page of Mathematica that I almost had to put a slide for that to show all the details. But basically, that's first order perturbation analysis. Okay. So it's a standard technique. And by the way that's derived, it's derived in a way that pops out the first order calculation of the energy, which is what physicists want, right? But in the derivation, it assumes that there's a modified wave function. You don't ever have to calculate it. You can get the energy term out without ever having to compute the wave function. And boy, do we love that, because we save all that computation and we get the answer we want with a formula that is very easy to apply. So that's part of the problem. Because that technique is so convenient, effective, that you don't ever have to compute the wave function. Who needs the wave function? Right? I'm saying let's go get it anyway. It might be good for something. Okay, so. But that's exactly how all of these were computed. But now that we know what the energy is, now we can actually use it to go back and compute what the wave function is. So I've done that. You have to do it numerically. There's no closed form for it. So given a charge distribution, and I'll use the Gaussian one as the example. For me, that seems most physically plausible. So I'll pick one and use it. But I think you can see from the previous slides that it wouldn't have mattered which one I chose. They would all lead to similar conclusions. And I've actually tested it on one of the other ones. So I'll assume Gaussian and its corresponding modified potential. Can we find the modified Dirac equation function? Now, solving this kind of thing numerically is there's a known technique for doing it. A guy named Hammerling and his co-authors in 2010 developed a two-sided shooting method. So basically, if you've got the differential equations, this was down here is the original differential equations that I pointed out, the two first-order radial equations. You got the boundary conditions at infinity and the normalization condition. So this is the basic problem. You can solve that by doing forward integration from the inside out and from outside in. And then what you do is, the first time you do that, you end up with a solution that goes this way and a solution that goes that way, and they don't match in the middle. So you say, okay, they do hit here, but the slopes are wrong. So now you adjust the slope conditions at the end until finally they now agree in the middle. That's the two-sided shooting method for adjusting the free boundary conditions until they agree from both sides. Hammerling et al. Did that for the Schrodinger problem, but they didn't do it for Dirac. So I extended it, and it wasn't too hard to extend it into the Dirac form. But as far as I know, I haven't seen anybody in the literature actually do that. So it could be that this is technically a new contribution, extending this two-sided shooting method into the Dirac formulation. Nonetheless, so I did it. This is now the modified form. The modification basically means you have to have a modified Coulomb potential, and you have to have a modified energy term. This is the energy term. That's the potential term, the E minus V. And when you put in the modifications, there's the little incremental, the 1 part in a million energy expectation that we have for the change. And over here is the modified Coulomb potential, which in the case of the Gaussian led to an ERF function. So ERF basically is 1 everywhere except for a little round off at the origin. So basically it's unchanged from normal Coulomb except near the origin. It rounds down. So this is the thing that had to be solved numerically. So I solved it, and now I'm going to show you a conceptual picture of what it looks like, and then I'll back that up with the detailed mathematical pictures. The reason I'm going to do it that way is because you can't show just one picture. It's too complicated, and the scales, it's a stiff problem with too many scale dimensions, too many varieties in scales. So I'll show you the concept, what the solution looks like, and then I'll back it up with the math really gave that. So we've been talking about the e to the minus r form of the ground state solution. That's shown in red here. There's our e to the minus r going off in positive direction and negative direction. And that has the cusp or the singularity at the origin. The new solution has the form of a rounded top. Instead of a pointy top or a singular top, it rounds it off at the top. That's what you'd expect. It has to have a slope continuity at the top. And the final solution ends up being lower than the original charge density. So what that means is charge is lost near the peak because it's no longer coming up to its full singular potential, singular charge density. So we round off and we lose a little at the top. What that means is, if it was a hill of sand, you take some sand off the top, but sand is preserved, it better get shoved down the shoulders of the distribution. So you lose charge near the peak, and you displace it down the sides. And what the numerical solution says, you lose a 1 part in a million at the top, and it gets shifted down the sides on this wafer-thin layer. You know, it's so thin that I have to exaggerate it to plot it for you. But this is the look of it. Now, so we lose top charge there, distribute it down the sides. If you look at the difference function, you see something, a difference wave function that looks like this. Here we're showing that we've lost charge there and we've distributed it down the sides. So if you keep that in mind, now here's what the mathematical results gave. If you look at this plot here, this is the one that corresponds to the peak version of the top. You see that the numerical solution is rounded at the top, doesn't have the singular wave function. So it's showing what I showed before, except that if I was to plot it to scale, it would all be happening in the top pixel up there. It's super tiny. It's happening at 0.998. That would be where that's a scale of 0 to 1, so it would be in the top pixel. Super tiny effect. And now if you go look at the distribution down the sides, this plot here, the green curve here, corresponds to this part of the difference wave function down here. And you see that it's showing that, yes, some charge is lost there, and we know the amount. And then this curve here is the part that's distributed down the sides. That little area there corresponds to that shape there. But what it's saying is you have to go a factor of 1,000 1,000 out to get it, and it's really, really tiny. Okay? So it's consistent with the picture I did. It's just now on the scale. Finally, this picture, what I've been showing you here is the charge densities, the rho. But in fact, to do the computation, you have to use the wave function, the upper and lower components, f and g. And you have to do the two-sided shooting method and the two-point matching in those terms. So this is actually just showing how the calculation was done. I really did have two matching points in the shooting direction from both in and out. So that was actually done that way. Finally, so the charge distribution basically has a rounded top. What this last plot is showing is the upper component, f, also has a rounded top, but the lower component does not. The lower component actually gets driven to 0 at the origin. Now that's interesting and important. What you might have expected was everything has a rounded top, including the lower component. What this is saying is the lower component goes to 0. The lower component is the negative energy part, the positron component. So it says normally the prediction of the Dirac equation is that there's a large electron component and there's a small positron component. But when you do the Lamb shift calculation and the corresponding wave function, that positron component vanishes at the origin. That, I think, is important.
That's being repelled by the proton.
Right. And so you could certainly justify it because it's opposite charge, so that would make sense. It's being repelled in a way that wasn't modeled previously. However, so yes, it feels right that it must do that. Okay. But this is, for the first time, this is saying that that's happening. Now, I think that's also a new result. Because no one's ever computed the wave function, no one has said that the upper and lower component behave differently in the limit as you get close to the origin. And that may be suggestive of some deeper physics. So finally, to summarize then, we open the talk with, is there some wave function? And the mystery is, what does the function look like? Now, here's the summary of the picture. It has a rounded top in the density, and the large component has a similar rounded top, and the small component is driven to 0 at the origin. So that's a summary of the qualitative behavior. Final discussion on that, then, the exponential charge distribution. The other distributions that I tried, I actually tried it for the exponential distribution. It behaved the exact same way. Rounded top, small component driven to 0. So the conclusion, at least at that level, seems to be general. I believe we would get the same thing for the other distributions, but I haven't proven it. One other last note about this. Dick, you remember when I spoke to you about a year ago? I was working heavily on, not on the numerical methods, but on analytic methods, because I was trying to, can I do what Dirac and Schrodinger did and get a closed form analytical solution for these curves? Wouldn't that be wonderful if I could? And Dick said, basically, can't you just do this numerically and be done in an hour or so? And that was really good advice. It speeded me up tremendously by focusing on that. So I still have that result. Yes, you can, and they turn out to be confluent hypergeometric functions is the way to compactly describe those. So there's another whole paper there with some nice math, but now I could write that paper because I have the numerical results that really allowed me to find what was going on. Now, I'm slightly over time. Shall I just wrap up?
Yeah, we have the room, but people may need to leave.
Yeah,
you can keep talking and people can leave.
Yeah, so why don't I say formally the talk ends now, and if there's any questions from people that are remote, we could take them. There's a couple more things that are worth saying, but we can formally wrap up now.
Yeah, questions?
I'd like to hear about the implications.
Okay, great. So we'll follow further. Any other questions from anybody before I continue? Okay, so we have the thinking that we have now is the electron is behaving not like a point. It's behaving like a moving point. The scattering experiments still say that it behaves like a point. You slam anything at it, and you look for the radius at which it just barely misses. It's as small as you can go. It still looks like a point. But it's behaving like a moving point. And the motion has this small distribution. That's when I talk about charge distribution. I'm not saying that it's not behaving like a point. I'm saying it's behaving like a moving point with a Sub-Compton motion. That's what this appears to say.
I'm going to go get Paul.
The way that we're analyzing this is all based on the Lamb shift. Well, the Lamb shift is a bound state. It's coming from bound state. Basically, it's coming from looking at the energy level transitions from n=2 state to n=1 state, right? So technically, that's not telling us something about a free electron. It's telling us about a behavior that we can measure and we can reason about when it's in the context of moving around near the atom, near the nucleus of the atom. Right? So what this next couple of slides is to try and make the link between what it looks like we can say with some confidence about when the electron is near the nucleus. That's what we've talked about so far. But could we extrapolate that to the free electron case? In particular, my hypothesis is if it's behaving like a jittered point charge, when we can catch it near the nucleus and measure its energy effectively that way, does it also behave that way as a free electron? To foreshadow, I believe it does. In fact, the way that QED calculates the Lamb shift gives us a hint that there's effectively a way to make a continuity between its behavior in the tightly bound state and the free state. And the linkage between those is the Bethe logarithm. Bethe is Hans Bethe was the physicist in the 1940s who took the first major step towards quantum electrodynamics. Feynman followed it up Feynman, Schwinger, Tominaga followed it up. But Hans Bethe from Cornell was the guy who had the first insight about being able to calculate what the Lamb shift would be. So this is the formula I showed on the first slide, the leading term of the Lamb shift. And all of these things are physical constants, you know, mass, speed of light, a fine structure constant. But what about this one, K naught? So what is K naught? That's the Bethe logarithm. And Bethe, in his 1947 paper, sort of gave this very hand-wavy argument about how you would compute this, and then pulled that number out of his ear, apparently. I mean, from the paper. He said, you can compute this, and with thanks to Miss Sten, I think it was, you know, our assistant in the computer department in Cornell, thanks to her, we pulled this number out, and it's like 16.7. And just leaves it at that. So, you know, utterly unsatisfactory. How you couldn't duplicate that work based on what he said. And it wasn't until 1951 that he wrote another paper, Bethe, Brown, and Sten, that they explain actually how to do the calculation. And they correct it. It wasn't 16.7, it was 17.8, or something like that. So they got a close estimate, but it wasn't quite right. And they never did explain how they did it, until 3 years later they did. And then Bethe and Salpeter wrote a book that also described it in more detail. So it's a detailed calculation that's very hard to do, and it's particularly hard to do with high precision. So it was remarkable that they could do it in the 1940s. Nowadays, you know, we have amazing precision measurements. Guys like Genshura and Moore at NIST, you know, National Institute of Standards, they're now the keepers of the physical constants. And they, among other things, like giving us corrections to the mass of the electron, you know, the eighth digit of the mass of the electron, what the fine structure constant is, they also tabulate the Bethe logarithm. And this is the table from their chart where they computed this thing. And evidently, it's a science in itself to compute this Bethe logarithm. So now, you need to know that in order to be able to compute the Lamb shift. But take a look at what's in the table. I mean, I didn't just put it up here to be sort of intimidating or, you know, bowl people over with this table of numbers. Take a look at it. 2.9, 2.8, coming down to 2.7. It's all 2 point something, 2.7, 2.8. I'm going to plot it for you here. Here's a plot of
2.81177, by the way, is the natural log of 16.7. So that was the number.
Yeah, right. Yes, exactly. So they were
2.738308.
That's the corrected number that they got in 1951. I think they said it was 17.7 or something in the first paper. So they were wrong. They got a poor estimate then, and 3 years later they had a better estimate, which is now consistent with modern tabulations of it. Okay. So, but now the K naught term there that they quote in the table is now, I'm now plotting it here, and you see that it goes from 2.70 is its final resting value at n equals infinity. What is n equals infinity? It's kind of like a free electron. You're now such a high energy state away from the nucleus that you've nearly vaporized or ionized. You're now nearly a free electron. So n equals infinity approximately corresponds to the free electron state. And as the electron becomes more and more tightly bound into the n equals 2 and n equals 1 states that we've been talking about, this value goes up. Now, what I believe that's saying is that jittery motion of the electron that's causing the Lamb shift when we get it close to the nucleus, the size of that jitter is basically staying the same even when we come out here. It's a constant amount of jitter. It changes only by a few % when you bring it in. That's kind of what we're looking for, is a kind of a physically constant behavior. It does change, but only by a few % when you get it close to the nucleus. Oh, hang on. Wait a minute. I thought I plugged my... Is that better? Let me just check here. Okay, charging now. Okay, so now they put in the table that value is basically 2.7-ish it goes up by about 0.2 or so. So on that scale, it appears to change by about 10%. Okay? But that's the number that they put in the table. The number that's actually used in the equation is not ln of k naught over the Rydberg constant. It's ln of mc squared over k naught. So when you take that into account, you scale by the factor of the Rydberg constant times it over mc squared, the actual value that you're using in this calculation is this term, ln of mc squared over k naught. And now I'm plotting that here. That now takes a value of 7.8, and it has the same additive variation, about 0.228 or so, 226. So that means the quantity that we care about is changing by only 3%, 3.3%. I think what that says is that the distribution of charge that we can measure and reason about in the lamp shift case holds true to within 3% when you take it all the way out to infinity.
Maybe when it's in close, it's distorted, tidal distortion or something.
Right, exactly. Some sort of distortion because it's now being in the influence of this strong force, this not strong force, but this nearby force. So the tidal influence is a nice metaphor for that. Right. That's exactly what I'm saying. So the tidal effect is sort of a 3% effect, but because we have the benefit of the lamp shift of the Bethe logarithm calculation, I think this builds a bridge from the bound states to the unbound and therefore free states that would allow us to extrapolate that the Sub-Compton charge distribution that applied to the lamp shift should also apply to a free electron. So that's a hypothesis of mine. I can't prove it. I've given you my reasoning, and I sort of have a question mark. I'd like to. One of the things I want to do with it, if I'm able to promote this work a little bit, I'd like to fly out to Washington and talk to Gensura and Moore and ask them. They're the ones who've done that calculation. Would they agree with this reasoning that this is telling us something about a free electron? I have the feeling that they would have a strong opinion about it, and it might be negative, but they would say, I'm pretty sure, either yes, that's a good idea, or no, and here's why. They might be among the few people who could really have a strong opinion about it. One of the last comments here. We had several candidate distributions. And my point of showing all the candidates is to emphasize, I don't know what the actual distribution is, but they all behave similarly, and they all seem to obey the same constraints. But what would make this really finished work would be if there was some way to actually determine what the real distribution is. Maybe it really is Gaussian. Maybe it looks a little bit like Gaussian with a little bit of ring behavior added onto it. Who knows what it could be? It could be anything, right? But what I do think is that there is a way to calculate that thing. I just don't know what it is yet. And that's why I'm showing it as a question for Gensura and Moore. They're the ones who have computed the Bethe logarithm. That calculation, this is a lot like Parseval's theorem and Fourier transforms. They've got, that calculation is a big sum of energy components. It's kind of like a spectrum, an auditory spectrum. You got all these things. The thing about this kind of spectral analysis, you can get the energy two different ways. You can add up the squares of the samples, or you can add up the Fourier components. That's Parseval's theorem. You can do it in the frequency domain or the time domain if it's audio. In the physics case here, you can do it in the spatial domain, or you can do it in the momentum domain. That's the Fourier transform, and they're doing that calculation in the momentum domain. They never convert it into the spatial domain, which is effectively what I'm doing. Now, what I've done is I've shown that candidate distributions in the spatial domain that have the right energy, the same total energy, can agree, but they know what the Fourier coefficients are. Now, if they knew what the phases are, they could actually add them up. It would be the equivalent of reconstruct the wave function with the waveform from the spectrum. They're in a position to do that calculation where it was going to take me a year to even figure out how they were doing their calculation. So this is a case for collaboration. You collaborate with the guys who already know how to do it. It was beyond what I was going to be able to do. But that's a question for them. Could they actually determine what that function is? So they would first have to agree that it makes sense to look for it. But if they agreed with it, they would be the guys who could actually say definitively what the shape is. So I want to get on a plane to Washington and ask these guys if they would take a meeting. I would ask them if they would be interested in doing that. So that's effectively the end of the main body of the talk. I have one other a short video to play. Do we still have?
We still have the room, and we're still recording.
Okay, still recording.
And we still have some remote people online. Yes.
Okay.
Three of them.
Well, so tell you what, it's a slow-moving animation. That I think that so they're going to get every 10th frame or something.
I don't know. We'll see how it goes.
Let's try. So
we'll get whatever they get.
Oh, that's true. No, you won't. I'm going to turn my computer sideways here. So,
screen here.
yeah, you guys can see a little better. Sorry. Okay. Oh, and I guess now audio. So this is not the. This is the speed. All right, no, that's not going to work. All right, so then I'll just show it. Show it as is. So the Dirac equation gave the upper and lower component, and I said that those were spinors. That is a notoriously tricky thing. It looks like a four-dimensional vector. There's four components in it, but I wrestled with this for a while before Shusheng Zhang at Stanford pointed out to me, you're thinking about it like it's a four-dimensional vector. It's not. It looks like a vector. You're writing it like a vector, but it's two pairs of quantities, and those are spinors. Those are Pauli spinors. They're not vectors. Now, what's the difference between a vector and a spinor? That's the purpose of this little visualization. I don't think too many people have a gut feeling for what a spinor is. The purpose of this is to show what a spinor is. Spin 1/2 has some unique properties, and so here it is. Demonstration of spin 1/2. I'm going to show you what spin 1/2 looks like with a physical model. I'm narrating over the video that I shot, and we'll put it on. So an ordinary object has the simple property that when you rotate it through 360 degrees, it looks the same as when you started. That's a normal, ordinary object. But this strange object has the property spin 1/2. When you rotate it through a full turn, it doesn't look the same as when you started. Now you're off by pi/2. You got to rotate it through a second turn before you get back to where you started. That's what spin 1/2 is. You have to rotate twice to get back to where you started. An electron has spin up and spin down, which we can simulate by tilting that outward disk, either tilting it down or tilting it up. But it's just because we've done the tilt at 45 degrees, we still have the spin 1/2 property. You have to go around twice before you get back to where you started. So one of them is tipped down, the other one's tipped up, and now you still have to go around twice because they still have the 2-to-1 gear ratio. So both of those are models of spin 1/2, but they're different from each other because one's tipped up and the other's tipped down. That's spin up and spin down. You see those little arrow vectors. That shows the typical undergraduate diagram that shows the precession of the spin vector around the axis of quantization. That's why I tipped them that way. So this is a model of what's in the physics textbooks to explain it to you, but nobody ever shows you that it's got this got to go around twice property. So those are the Pauli spin vectors. So that's my way of showing Pauli's notation for this. Now, a positron is basically an electron with a time-reversed electron. Well, so now the positron is rotating in the opposite direction. So it's an orthogonal component. Positron and electron look the same, but they're spinning in opposite directions. And now we have the four components of the four separate components. Now they're rotating all together, and it's kind of takes a little getting your head around it to look at them, but you can see they're all different from each other. Spin up, spin down, spinning left, and spinning right. That's why you have four of them. Now see, those are the Dirac spinor components. And now finally, just kind of, now I spin them a couple of times just so you can see that's the basis functions for the Dirac equation. Now, if I didn't show you this picture, I just said, here's the math and there's the matrices, what would it mean? It would be very difficult to imagine what is implied by that. But this gives you an idea of rotating in opposite directions because of negative energy, and spin up and spin down. This next quote here from Feynman. In his Nobel lecture at 65, Dirac obtained his equation for the description of the electron by an almost purely mathematical proposition. A simple physical view by which the contents of this equation can be seen is still lacking. What he was saying, even in 65, getting his Nobel lecture, he said basically, this thing is so complicated, even I can't understand it. There's no simple way to think about it. A simple physical view is still lacking. That's the purpose of this little demonstration, is to try to give a simple physical view for what the four components of the spinors look like. The radial part's pretty easy to understand. It's exponential distributions with rounded tops. But that spinning thing, it's a brain buster. And I think that could be helpful.
That's very cool.
Thanks. Okay, so now I really stop.
All right, thanks, Lloyd.
Thank you.